Welcome to Science for Sleep. Tonight, we drift into one of the deepest mysteries ever uncovered, the nature of space-time itself. Tonight, we ask a quiet but unsettling question. If space-time holds the entire universe together, why don't we truly understand what it is? We can measure it. We can bend it in equations. We can detect its ripples from colliding black holes billions of light years away. And yet, when we ask what space-time actually is, whether it is something physical, something emergent, or something even more fundamental, our certainty dissolves. To understand why this mystery still remains, we have to begin in a world where everything once felt simple. Before Einstein, before curved geometry, before time could stretch and space could bend. For centuries, the universe was described as a vast and orderly machine. At its heart stood Isaac Newton's vision of reality, a cosmos built upon absolute space and absolute time. In Newton's universe, space was like an infinite stage. It existed independently of the objects within it. Stars, planets, comets, they moved across this stage. But the stage itself never moved. It was fixed, eternal, unchanging. Time, too, was absolute. It flowed uniformly everywhere in the universe, like a perfect cosmic clock ticking the same for all observers. A second on Earth was identical to a second on Jupiter. Past, present, and future were universal concepts shared by every point in existence. This framework was powerful. It worked. Newton's laws predicted planetary motion with extraordinary accuracy. They explained falling apples and orbiting moons using the same mathematical principles. Gravity, in this view, was a force, an invisible pull between masses acting instantly across distance. The universe appeared stable, mechanical, predictable. Space was a container. Time was a river. Matter moved through both. For over 200 years, this model went largely unchallenged. It described cannonballs, ocean tides, and planetary orbits with astonishing precision. The cosmos seemed fully mapped. But beneath that stability, cracks were forming. Light, unlike ordinary objects, behaved strangely. Experiments in the 19th century revealed something unsettling. No matter how fast you moved, light's speed remained constant. Whether you chased it or moved away from it, and it always traveled at the same speed, approximately 300,000 kilometers per second. This fact did not fit comfortably within Newton's absolute framework. If space were truly fixed and time truly universal, then speeds should add together in simple ways. If you ran forward on a train and threw a ball, the ball's speed would combine with your own. Why then did light refuse to obey this rule? Physicists attempted to explain this anomaly by proposing an invisible substance called the ether, a medium through which light waves supposedly traveled. But careful experiments failed to detect it. The ether seemed not to exist. And so, by the late 19th century, physics faced a quiet crisis. Space and time, once unquestioned foundations, were no longer fully secure. Into this uncertainty stepped a young patent clerk in Bern, Switzerland. But before Einstein would overturn centuries of certainty, it is important to understand the psychological weight of Newton's universe. It offered comfort. In a cosmos governed by absolute space and absolute time, reality was stable. There was a universal present moment shared across the stars. There was a fixed background against which all motion could be measured. Cause and effect unfolded in a predictable, linear fashion. It was intuitive. It matched human experience. When you look around, space appears still. When you feel time passing, it seems steady and uniform. Newton's universe aligned with everyday perception. But nature, as it often does, was preparing to reveal something stranger. The constancy of light's speed hinted at a deeper truth, one that would force physicists to abandon the idea of absolute space and universal time entirely. And when that happened, the stage itself would begin to move. Time would stretch, lengths would contract, simultaneity would dissolve, and space and time would merge into something new, something we now call space-time. But even that revolutionary concept would not be the final answer, because over a century later, despite our equations and our observations, we still cannot say with certainty what space-time truly is. Is it fundamental? Is it emergent? Is it continuous or made of tiny discrete pieces? Or is it something even stranger than our mathematics can yet describe? Tonight, as we begin this journey, we leave behind the comfortable world of absolute certainty. We step into a universe where the stage itself bends, where time does not flow equally for all, where the fabric of reality can ripple, and where the deeper we look, the more mysterious it becomes. Before space-time curved, it stood still, when light refused to obey. At the end of the 19th century, physics seemed almost complete. Newton's laws described motion. Maxwell's equations described electricity, magnetism, and light. The planets followed predictable paths. The stars appeared fixed against an unchanging background. Many scientists believed only small details remained to be refined. But it is often in the smallest details that reality begins to unravel. The problem began with light. According to classical physics, speeds should combine. If you walk forward at 5 kilometers per hour on a moving train, traveling at 50 kilometers per hour, your speed relative to the ground becomes 55. Motion adds together. So if light travels at a certain speed and you move toward it, you should measure it traveling slightly slower relative to you. If you move away from it, you should measure it slightly faster. But experiments refused to agree. In 1887, Albert Michelson and Edward Morley performed an experiment designed to detect Earth's motion through the supposed ether, the invisible medium believed to carry light waves. If Earth were moving through this medium, light traveling in different directions should move at slightly different speeds. But no difference was found. Light's speed remained constant. No matter the direction, no matter Earth's motion, no matter the observer. This was deeply unsettling. If space were absolute, as Newton believed, and time were universal, then the speed of light should vary depending on motion. But it did not. There were only two possibilities. Either the experiments were flawed, or our understanding of space and time was wrong. For years, physicists attempted to preserve the old framework. Some suggested that objects physically contracted as they moved through the ether. Others proposed increasingly complex explanations, but none felt satisfying. Then, in 1905, a 26-year-old patent clerk named Albert Einstein proposed something radical. What if the speed of light is truly constant for all observers? Not approximately constant, not conditionally constant, but universally constant. And what if the laws of physics are the same in all inertial reference frames? If both of these statements are true, then something else must give way. That something was absolute space and absolute time. Einstein realized that if light's speed never changes, then measurements of space and time must adjust to preserve that constancy. Time could no longer be universal. Space could no longer be fixed. They had to become flexible. This idea formed the foundation of special relativity. According to Einstein, time does not tick at the same rate for everyone. If you move close to the speed of light, your clock slows down relative to someone at rest. This effect is known as time dilation. Similarly, lengths contract along the direction of motion. A moving object appears shorter from the perspective of a stationary observer. Even simultaneity, the idea that two events occur at the same time, becomes relative. Two observers moving relative to each other may disagree on whether events happened simultaneously. This was not philosophy, it was mathematics, and it was experimentally verified. Particles moving near the speed of light live longer than stationary ones because time slows for them. GPS satellites must account for relativistic time dilation to function accurately. Space and time, once considered rigid and absolute, had become elastic. But Einstein did not stop there. In 1908, Hermann Minkowski reformulated Einstein's work into a geometric framework. Instead of thinking of space and time separately, Minkowski combined them into a single four-dimensional continuum, space-time. 3 dimensions of space, 1 dimension of time, interwoven. In this view, your events are not just located in space. They are located in space-time. Motion becomes a path through this 4-dimensional structure. The speed of light remains constant because it represents the geometry of space-time itself. Light does not move through space and time in the old sense. It follows the structure of space-time. This was revolutionary, but it also deepened the mystery. If space and time are not fixed backgrounds, what are they? Are they physical substances? Are they relationships between events? Are they mathematical descriptions? Special relativity solved the problem of light's constancy. It explained why time slows and lengths contract. But it left open a deeper question. Why does space-time behave this way? What is it made of? Is it smooth and continuous? Or does it have a microscopic structure? By redefining space and time as flexible, Einstein did not eliminate mystery. He transformed it. The stable stage of Newton's universe had dissolved. Space could stretch, time could bend. Observers could disagree. Reality was no longer absolute. And this was only the beginning. Because if space-time could stretch and contract due to motion, perhaps it could also bend under the influence of mass. And if that were true, then gravity itself would not be a force at all. It would be geometry. And with that realization, space-time would become even stranger. Before we continue, take a slow breath. If you enjoy slow, thoughtful science like this, consider subscribing, not for noise or hype, but for quiet journeys into the deepest ideas in physics. Now, imagine holding a heavy bowling ball in your hands. According to Newton, the ball pulls on the Earth with a force. The Earth pulls back. Gravity is an invisible attraction acting across space. But Einstein began to wonder something radical. What if gravity is not a force at all? What if nothing is pulling? What if space itself is bending? In 1915, Einstein completed his theory of general relativity. It proposed something extraordinary. Mass and energy do not pull objects through space. They curve space-time itself. Planets are not being tugged by invisible forces. They are following the natural curves in space-time. Imagine placing a heavy sphere on a stretched rubber sheet. The sheet bends. Now roll a smaller marble nearby. The marble moves not because the sphere pulls it directly, but because the sheet beneath it is curved. This analogy is imperfect, but it captures the idea. The sun bends space-time. Earth follows the curve. Gravity is geometry. Pause for a moment and consider this. If space-time can bend, what is it bending into? If it curves, what is it made of? Is it a fabric? Is it physical? Or is it something purely mathematical? Einstein's equations described curvature with breathtaking precision. They predicted the bending of starlight around the sun. They predicted black holes. They predicted gravitational waves, ripples in space-time itself. And over the last century, every major prediction has been confirmed. But here's the deeper mystery. We can describe how space-time curves. We can calculate its geometry. But we do not know what space-time actually is. Is it fundamental? Or could it emerge from something deeper, like temperature emerges from atoms? And if space-time can ripple, stretch, and curve, does it have atoms of its own? Tiny building blocks too small for us to see. This is where understanding begins to fade. General relativity treats space-time as smooth and continuous, like a perfectly polished surface. But quantum physics tells us that at the smallest scales, reality is not smooth at all. It is grainy, fluctuating, uncertain. So which is it? Is space-time smooth, or is it quantum? This conflict is one of the greatest unsolved problems in science. And as we move deeper, the mystery only grows. So stay with me. If space-time can bend, then we must ask how far that bending can go. Einstein's equations describe gravity as curvature, and for most of the universe, that curvature is gentle. Planets follow smooth arcs around stars. Light bends slightly when passing massive objects. Even neutron stars, incredibly dense remnants of collapsed suns, curve space-time in ways that remain calculable. But there exists a region where curvature does not remain gentle. There exists a place where space-time folds inward without limit. Black holes. When a massive star exhausts its nuclear fuel, gravity takes over completely. The star collapses under its own weight. If the mass is great enough, no known force can stop the collapse. The result is not simply a dense object. It is a region where space-time itself curves so intensely that not even light can escape. At the boundary of a black hole lies the event horizon. This is not a surface you can touch. It is a threshold in space-time, a point of no return. Once crossed, all paths lead inward. Not because something pulls you like a rope, but because space-time itself has curved in such a way that every possible direction leads toward the center. And at the center lies something even more unsettling: the singularity. According to Einstein's equations, if you trace the curvature inward, density increases without limit. Space-time becomes infinitely curved. The mathematics predicts a point of zero volume and infinite density. But infinity in physics is usually a warning sign. It suggests that our theory has reached the edge of its validity. The singularity is not proof of infinite density. It is proof that general relativity breaks down. Here is the quiet tension at the heart of modern physics. General relativity describes the large-scale structure of space-time with extraordinary precision. Quantum mechanics describes the behavior of particles at the smallest scales with equal success. But when we try to apply both theories simultaneously, inside black holes or at the beginning of the universe, they refuse to cooperate. General relativity assumes space-time is smooth and continuous. Quantum mechanics tells us that at very small scales, nature is discrete and probabilistic. At the Planck scale, roughly 100 billion trillion times smaller than a proton, space-time itself may no longer behave as a smooth fabric. It may fluctuate. It may foam. It may lose all recognizable structure. If space-time has a smallest unit, we have not yet detected it. If it is made of something more fundamental, we do not yet know what that is. We can calculate how space-time bends, but we cannot say whether it is composed of tiny building blocks or whether it is an emergent phenomenon arising from deeper physics. And this is where the mystery deepens. Inside a black hole, quantum effects should become important because of the extreme curvature. But we do not possess a complete theory that unites quantum mechanics with gravity. We call this missing framework quantum gravity. It is one of the greatest unsolved problems in science. Without it, we are left with two powerful but incompatible descriptions of reality. One governs the very large, the other governs the very small. Space-time sits uncomfortably between them. Consider this carefully. If space-time can curve infinitely, does that mean it tears? If it fluctuates at microscopic scales, does that mean it has a texture? If it emerges from something deeper, what is that deeper layer made of? These are not philosophical curiosities. They are scientific necessities. To understand black holes fully, to understand the earliest moments of the universe, to understand gravity at quantum scales, we must understand what space-time actually is. For now, we only understand its behavior. We know it bends near massive objects. We know it stretches for moving observers. We know it ripples when black holes collide. In 2015, gravitational waves were directly detected for the first time. Subtle distortions in space-time passing through Earth after traveling billions of light years. The detection confirmed that space-time is dynamic. It can move. It can vibrate. But what exactly is vibrating? When a gravitational wave passes, space itself stretches and compresses by unimaginably small amounts. If space-time were purely abstract, what would it mean for it to stretch? If it were made of something, what is that something? The closer we look, the less solid our understanding becomes. At everyday scales, space-time feels stable and reliable. At cosmic scales, it bends predictably. But at extreme scales, inside black holes and at the birth of the universe, it becomes unstable in our equations. And perhaps that instability is a clue. Perhaps space-time is not fundamental at all. Perhaps it emerges from something deeper, something we have not yet discovered. Even after Einstein's remarkable realization that light's speed is constant, and that time and space must adapt to preserve that constancy, physicists still described space and time as separate concepts. Space was still thought of as a three-dimensional stage, and then time as an external flow marching uniformly forward. But this view couldn't fully capture the deeper structure revealed by special relativity. It wasn't until a German mathematician named Hermann Minkowski stepped into the picture that space and time were understood as a unified whole. In 1908, Minkowski showed that the mathematics underpinning Einstein's special relativity could be reformulated into a four-dimensional geometric continuum, where one coordinate represents time and the other three represent space, all intertwined into what we now call space-time. Minkowski famously declared that space by itself and time by itself are doomed to fade away into mere shadows, meaning that neither exists independently in the relativistic universe. Only their union has physical meaning. In this structure, each event is not merely a point in space or a tick in time, but a point in space-time that has both spatial and temporal coordinates. Minkowski's spacetime preserves the invariant interval, a combination of space and time separation between events that all observers agree upon, regardless of their motion, which became a cornerstone of modern physics. This change was more than a mathematical convenience. It redefined how the universe is structured. Instead of imagining space and time as separate backgrounds on which events unfold, physicists began to see reality as a four-dimensional tapestry where distance and duration are inseparable and where motion, timing, and geometry are intimately linked. Space-time, in this sense, is not a static stage. It is a unified framework that underlies every event in the universe. Whether it's a beam of light traveling across the cosmos or a clock ticking on Earth. This geometric view made rigorous what Einstein's relativity suggested: that the measurements of space and time depend on the observer's state of motion, yet the fundamental space-time interval remains invariant. But while space-time describes how events relate to one another across space and time dimensions, it does not tell us what space-time is in a deeper physical sense, whether it is something fundamental or emergent. Some contemporary ideas in theoretical physics propose that space-time might emerge from even more basic phenomena, such as quantum entanglement, hinting at underlying layers of reality we have yet to fully understand. As Minkowski's insight transformed special relativity into a geometric universe, and it set the stage for the next revolution. A theory where gravity itself becomes geometry, not force. And as profound as that change was, it still leaves a deeper mystery unresolved. What space-time fundamentally is? This question will take us into the heart of gravity and beyond. But before we go there, we must first see how space-time becomes curved when mass and energy are present. Before Einstein, gravity was a force, an invisible tug between masses acting across space. But if space-time is a unified geometric fabric, as Minkowski showed, then gravity might not be a force at all. In 1915, after a decade of steady thought and mathematical refinement, Albert Einstein completed the next stage of his revolution, the general theory of relativity. In this theory, gravity is not something that pulls objects through space. Instead, one mass and energy tells space-time how to curve, and that curvature tells objects how to move. Imagine a stretched rubber sheet representing space-time. If you place a heavy ball on it, the sheet bends. If you then roll a smaller marble near it, the marble does not move because of an invisible pull, but because it follows the curvature created by the heavy ball. This is the essence of Einstein's insight. Einstein's field equations express this idea mathematically, showing how space-time curvature is directly linked to the presence of mass and energy. The more massive an object, the more it warps space-time around it. Our sun, for example, curves the space-time in its vicinity, and Earth moves along this curved geometry in what we perceive as an orbit. According to general relativity, orbiting is not caused by a force pulling Earth inward, but by Earth following the natural curved path that space-time defines. This conception of gravity was spectacularly confirmed in 1919 when Arthur Eddington's expedition observed starlight bending around the sun during a solar eclipse. Light that should have passed straight, but instead curved in precise accordance with Einstein's predictions. That experiment transformed general relativity from theoretical abstraction into empirical reality. General relativity replaced the familiar notion of gravitational force with a geometric tapestry. Space and time, merging into a single dynamic arena where objects move not because they're pulled, but because they follow the shape of space-time itself. Time runs more slowly near massive bodies. Light changes its path in response to curvature. Bodies' clocks tick differently depending on gravitational potential. These effects have been measured with astonishing precision. GPS satellites, for instance, must correct for both special and general relativistic time dilation, or their positioning would drift by kilometers each day. Yet even this elegant theory has limits. It describes gravity and large-scale structure exceptionally well. But it makes predictions, such as singularities deep within black holes, that suggest the theory breaks down under extreme conditions. The curvature of space-time becomes so intense inside a black hole that our equations tell us density and curvature become infinite, a clear indication that general relativity is incomplete. General relativity widened our understanding of space-time from passive backdrop to active participant. Dynamic, curving, shaping motion across the cosmos. But it also deepened the mystery. If space-time itself curves, what ensures its continuity? Does space-time have an underlying structure at the smallest scales? Can it be quantized like other forces? As we move forward, we will explore these questions in environments where space-time is bent most extremely, where gravity and quantum uncertainty collide, and begin to see why our understanding remains unfinished. There is a place in the universe where space-time bends so severely that even light cannot escape. It is not simply a dense object. It is not merely a collapsed star. It is a region where the geometry of reality curves inward without mercy. Black holes are not holes in the conventional sense. They are not tunnels or empty voids. They are the consequence of gravity overwhelming every known force. When a massive star exhausts its nuclear fuel, it no longer produces the outward pressure necessary to counterbalance gravity. The core collapses inward under its own weight. If the mass is sufficient, roughly more than 3 times the mass of our Sun, nothing can halt that collapse. And according to general relativity, that collapse does not merely compress matter. It compresses space-time itself. To understand this, we must momentarily leave behind everyday intuition. When we imagine gravity, we imagine pulling, something drawing something else toward it. But in Einstein's framework, nothing is being pulled in the classical sense. Objects move along curved paths because space-time itself is curved. Now imagine that curvature increasing without limit. Near an ordinary planet like Earth, space-time curvature is gentle, and you do not notice it. Your clock ticks normally. Light bends only imperceptibly. But as mass increases and radius decreases, curvature intensifies. Near a neutron star, the collapsed core of a massive star, space-time is already dramatically warped. Clocks on its surface tick more slowly than clocks far away. And if collapse continues beyond the neutron star stage, something more extreme forms. The event horizon. The event horizon is not a physical surface. It is not made of material. It is a boundary in space-time, the radius at which the escape velocity equals the speed of light. Beyond this boundary, every possible path through space-time curves inward. There is no direction that leads outward, not because something blocks the way, but because the geometry itself forbids escape. Pause and consider that carefully. Inside the event horizon, the future points inward. In normal life, the future always points forward in time. You cannot choose to move into yesterday. Time flows in one direction. But inside a black hole, according to general relativity, the inward direction toward the center becomes as inevitable as tomorrow. Moving inward is not a choice. It is embedded in the structure of space-time. What does that say about space-time itself? Is it merely geometry? Or is it something more tangible? As one approaches the event horizon, gravitational time dilation becomes extreme. To a distant observer, a clock falling toward the black hole appears to slow down. Light from the falling object becomes red-shifted, stretched to longer wavelengths, fading gradually. The object appears to freeze at the edge, never quite crossing. But from the perspective of the falling observer, nothing unusual happens at the horizon itself. There is no solid surface, no sudden wall. Space-time feels locally normal. It is only when tidal forces become immense, stretching and compressing objects, that the experience becomes catastrophic. This difference in perspective reveals something profound. Space-time is not absolute. It depends on the observer's trajectory. Inside the black hole lies what general relativity calls a singularity. At this point, curvature becomes infinite in the equations. Density becomes infinite. The known laws of physics cease to provide meaningful answers. But infinities in physics usually signal failure, not truth. They tell us our model has reached its limits. At the singularity, general relativity no longer gives a complete description. The smooth geometric space-time that Einstein envisioned breaks down under extreme conditions. And here, the central mystery reappears. If space-time is smooth and continuous, how can it compress into a singularity? If quantum mechanics governs the smallest scales of reality, why does general relativity ignore it? Quantum theory describes nature as discrete, probabilistic, filled with fluctuations. At extremely small scales, around the Planck length, energy and geometry may fluctuate violently. Some theoretical models describe space-time at this scale as a foam, constantly fluctuating due to quantum uncertainty. But general relativity treats space-time as infinitely divisible and perfectly smooth. Both theories work exceptionally well in their own domains, but they cannot both be fully correct at the same time. Inside black holes, both quantum effects and gravitational curvature should dominate. Yet we do not have a theory that unifies them. This missing theory, quantum gravity, remains one of the greatest challenges in modern physics. Black holes are not just astrophysical objects. They are laboratories. They expose the cracks in our understanding. They reveal that our most successful theory of gravity becomes incomplete under extreme curvature. And they force us to confront uncomfortable questions. What happens to information that falls into a black hole? Does it disappear? Stephen Hawking's work in the 1970s showed that black holes are not entirely black. Due to quantum effects near the event horizon, they emit radiation, now called Hawking radiation. Over immense timescales, black holes can slowly evaporate. If black holes evaporate, what happens to the information they swallowed? Quantum mechanics insists that information cannot be destroyed, but classical general relativity suggests it might be lost inside the singularity. This conflict is known as the black hole information paradox, and it remains unresolved. The paradox is not merely about black holes, it is about space-time itself. If information cannot disappear, then the structure of space-time must somehow preserve it. Some theories suggest that information may be encoded on the event horizon's surface, leading to the holographic principle. The idea that our three-dimensional universe might be describable by information encoded on a two-dimensional boundary. Others suggest space-time itself may emerge from quantum entanglement, that geometry arises from deeper informational relationships. If that is true, then space-time is not fundamental. It is emergent, like temperature emerging from atomic motion, like waves emerging from water molecules. Black holes may be showing us that space-time is not the base layer of reality. It may be a macroscopic phenomenon arising from deeper quantum structures. And this brings us back to our central question. Why don't we understand space-time yet? Because the deeper we look, especially in places like black holes, the more space-time stops behaving like a smooth fabric and starts behaving like something incomplete. We can measure its curvature. We can predict its ripples. We can calculate how it bends near massive bodies. But we cannot yet say whether space-time is continuous or granular. We cannot say whether it is fundamental or emergent. We cannot describe what happens at its deepest breakdown. Black holes represent the boundary of knowledge. They are not merely objects in space. They are places where space-time itself reveals its fragility. And in that fragility lies the clue. Perhaps space-time is not the final layer. Perhaps it is a shadow of something deeper. So far, space-time has behaved like a grand geometric structure. It bends around stars. It stretches near black holes. It ripples when massive objects collide. General relativity treats it as smooth, continuous, and infinitely divisible, like a perfectly polished fabric extending across the universe. But there is another theory. A theory that governs the smallest scales of existence. And this theory tells a very different story. Quantum mechanics does not describe a smooth world. It describes a world built on probabilities, fluctuations, and discrete units. At atomic and subatomic scales, particles do not have definite positions until measured. Energy is quantized. Fields vibrate. Reality is restless. If you zoom in far enough, far smaller than atoms, far smaller than protons, the calm geometry of space-time may no longer remain calm. At extremely tiny scales, around what physicists call the Planck length, approximately 1.6 times 10 to the power of minus 35 meters, the effects of quantum mechanics and gravity should both become significant. This is the scale at which space-time itself may begin to fluctuate violently. And here is the problem. General relativity assumes space-time is smooth. Quantum mechanics suggests nothing at fundamental scales is smooth. Which one is correct, or are both incomplete? At the Planck scale, quantum uncertainty should cause space-time to fluctuate. Energy fluctuations could temporarily distort geometry. The very concept of a fixed background may dissolve into something like a turbulent sea. What physicist John Wheeler once described as space-time foam. In this foam-like picture, space-time is not a smooth surface, but a constantly shifting structure filled with microscopic fluctuations. Tiny wormholes might appear and vanish. Geometry itself might flicker unpredictably. But this description is speculative. We do not yet have experimental access to these scales. They are far beyond the reach of current particle accelerators. We cannot directly observe the Planck regime. And so we are left with two incredibly successful theories that refuse to merge. General relativity works beautifully for planets, stars, galaxies, and black holes. Quantum mechanics works flawlessly for atoms, for molecules, and particles. But when we try to describe gravity at quantum scales, when we attempt to quantize space-time itself, our mathematics breaks. Attempts to treat gravity like other quantum forces lead to infinities that cannot be renormalized away. The equations diverge. Predictions lose meaning. It is as if space-time resists being treated as just another field. And this resistance suggests something important. Perhaps space-time is not like other fields. Perhaps it is not fundamental in the same way. Consider how temperature works. Temperature feels fundamental, but it is not. It emerges from the collective motion of countless atoms. No single atom possesses temperature. Temperature arises from the system as a whole. Could space-time be similar? Could it emerge from deeper microscopic degrees of freedom? If so, then trying to quantize space-time directly might be like trying to quantize a wave without understanding the water beneath it. Some approaches to quantum gravity attempt to preserve space-time as fundamental but quantized. Loop quantum gravity, for example, proposes that space-time is composed of tiny discrete loops, granular rather than continuous. In this view, space itself has a smallest possible unit. Other approaches, such as string theory, suggest that fundamental entities are not points, but tiny vibrating strings existing in higher dimensional space. Space-time geometry then arises from the behavior of these strings. Still, other ideas go further. Some researchers propose that space-time may emerge from quantum entanglement in certain theoretical models. The connectivity of space-time geometry appears directly linked to patterns of entanglement between quantum systems. If entanglement disappears, space-time itself may fragment. If entanglement strengthens, space-time geometry may become smoother. In this view, geometry is not primary. Information is. This is a radical shift. For centuries, we thought of space as the stage and matter as the actors. Now we consider the possibility that information may be the foundation, and space-time merely a manifestation of deeper informational structure. But we do not yet know. And that uncertainty is precisely why we do not fully understand space-time. The tension between quantum mechanics and general relativity is not just technical. It is conceptual. General relativity is deterministic and geometric. Quantum mechanics is probabilistic and algebraic. A general relativity describes smooth curves. Quantum theory describes discrete jumps. General relativity treats space-time as background. Quantum mechanics suggests backgrounds may fluctuate. When we attempt to apply both simultaneously, such as at the center of a black hole or at the moment of the Big Bang, neither theory alone suffices, and no complete replacement exists yet. This is not a minor gap in knowledge. It is a foundational divide. To unify quantum mechanics and gravity is to understand space-time at its deepest level. To fail to unify them is to accept that our description of reality is incomplete. So we stand at an unusual point in physics. We can detect gravitational waves traveling across billions of light years. We can measure quantum fluctuations inside laboratories. But we cannot yet explain how space-time behaves when both regimes overlap. And perhaps this is the true reason we do not understand space-time yet. Because space-time sits at the intersection of two great pillars of modern physics, and those pillars do not align. The smooth curvature of Einstein, the jittering uncertainty of quantum theory. Somewhere beneath them lies a deeper layer, and until we uncover it, space-time remains both familiar and mysterious, measurable yet fundamentally unexplained. There exists a scale so small that our current understanding of reality begins to dissolve. It is called the Planck scale, and it represents a boundary, not in space, but in knowledge. At approximately 1.6 times 10 to the power of minus 35 meters, the Planck length is unimaginably tiny. To reach it, you would have to shrink an atom by a factor of 100 billion trillion. At this scale, the smooth geometry of space-time described by general relativity can no longer be trusted. Why? Because at the Planck scale, quantum effects are no longer negligible. Energy fluctuations become so intense that the very fabric of space-time, if it is a fabric at all, may begin to fluctuate violently. In classical general relativity, space-time is smooth and continuous. No matter how closely you zoom in, it remains a differentiable manifold. You can always define smaller and smaller distances. But quantum mechanics tells us that uncertainty governs nature at small scales. Energy and position cannot both be precisely defined. Virtual particles appear and disappear in fleeting instants. If energy fluctuates and energy curves space-time, and then curvature itself must fluctuate. This leads to a startling possibility. At sufficiently small scales, space-time may not resemble a smooth continuum at all. It may resemble something turbulent and granular, a restless sea of fluctuating geometry. Physicist John Wheeler described this as quantum foam, a picture in which space-time constantly bubbles with microscopic distortions. In this foam-like state, tiny wormholes could flicker in and out of existence. Distances might lose precise meaning. The concept of a fixed background geometry could dissolve entirely. But here is the profound difficulty. We cannot directly probe this scale. The Planck energy required to examine space-time at such small distances is far beyond anything achievable with current technology. Even our most powerful particle accelerators operate at energies trillions of times too weak. The Planck scale remains experimentally inaccessible. So how do we proceed? Theoretical physicists attempt to construct mathematical frameworks that remain consistent at these scales. Some approaches suggest that space-time is fundamentally discrete, composed of tiny units, much like matter is composed of atoms. Loop quantum gravity, for example, proposes that space is quantized into finite loops or networks. In this view, there is a smallest possible unit of area and volume. Space-time is granular, not continuous. Other theories, such as string theory, suggest that the fundamental building blocks of reality are not points, but vibrating strings. These strings exist in higher dimensional space, and the geometry we observe emerges from their vibrational patterns. In this picture, space-time may not be fundamental at all. It may arise from deeper quantum structures embedded in extra dimensions. Yet none of these theories have been experimentally confirmed. And this is where the mystery intensifies. If space-time is discrete, what is the nature of its smallest units? Are they geometric? Are they informational? Do they obey quantum rules in the same way particles do? If space-time is emergent, what is it emerging from? Perhaps from entanglement, the strange quantum connection between particles that Einstein once called spooky action at a distance. Some recent theoretical work suggests that the structure of space-time geometry may be intimately related to patterns of quantum entanglement. In certain mathematical models, reducing entanglement between regions causes space-time itself to disconnect. This suggests something radical. Space-time might not be the foundation of reality. It might be a consequence. If so, then our question changes. Instead of asking how space-time curves, we must ask how space-time arises. The Planck scale represents a threshold where our intuitive notions of distance and duration may no longer apply. It is possible that below this scale, the concepts of before and after, near and far, lose operational meaning. If space-time is emergent, then at sufficiently small scales, there may be no space-time at all. Just a deeper layer of quantum relationships from which geometry eventually crystallizes. And this leads to an unsettling realization. Everything we experience, motion, gravity, light, causality, depends on space-time. If space-time itself is not fundamental, then everything we consider foundational may be derivative. We may be living within an effective description of something deeper. The Planck scale is not simply a tiny distance. It is a philosophical turning point. It marks the limit of where classical geometry ends and quantum uncertainty begins to dominate. It is where the smooth universe of Einstein dissolves into a probabilistic haze. And yet, even here, we do not have definitive answers. We have models, we have equations, we have beautiful mathematical constructions, but we do not have experimental verification. Until we can unify quantum mechanics with gravity in a consistent, testable way, space-time remains partially understood. We know how it behaves at large scales. We suspect it behaves differently at tiny scales. But we do not yet know its true nature. And perhaps this is why space-time continues to resist complete understanding. Because it is not merely a background in which physics happens. It may be the product of physics itself. If space-time is not fundamental, then what is? This question has led physicists into one of the most astonishing ideas in modern theoretical science. The possibility that our three-dimensional universe may not be fundamental at all. Instead, it may be a projection, a hologram. The holographic principle did not emerge from philosophy. It emerged from black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered something deeply surprising about black holes. When matter falls into a black hole, the black hole's entropy, a measure of its disorder or information content, increases. But what was extraordinary was not merely that entropy increased. It was how it increased. The entropy of a black hole does not scale with its volume. It scales with the area of its event horizon. This was shocking. In ordinary systems, entropy, and thus information, scales with volume. A larger box holds more information because it has more space inside. But a black hole behaves differently. Its maximum information content is proportional to its surface area, not its volume. This suggested something profound. Perhaps the information describing a region of space is not stored in its volume, but on its boundary. In the 1990s, physicist Gerard 't Hooft and later Leonard Susskind proposed a bold interpretation of this idea. They suggested that the entire universe might operate according to a similar principle. Everything happening within a volume of space could be fully described by information encoded on its boundary surface. This is the holographic principle. Just as a two-dimensional hologram can encode a three-dimensional image, our three-dimensional universe might be encoded on a two-dimensional boundary. In certain formulations of string theory, particularly the ADS/CFT correspondence, this idea becomes mathematically precise. A gravitational theory operating in a higher dimensional space-time can be equivalent to a quantum field theory defined on a lower dimensional boundary without gravity. In simpler terms, gravity and space-time geometry in one description can emerge from a non-gravitational quantum system in another. This equivalence is not metaphorical. It is mathematical. And it suggests something extraordinary. Or space-time geometry may emerge from quantum interactions. In these models, the curvature of space-time corresponds to patterns of quantum entanglement. When quantum systems are strongly entangled, the corresponding space-time geometry is smooth and connected. When entanglement weakens, space-time geometry can fragment. Some researchers have even proposed that space-time connectivity itself may be built from entanglement. The phrase EAR equals EPR, suggested by Juan Maldacena and Leonard Susskind, hints at a deep connection between Einstein-Rosen bridges, wormholes, and quantum entanglement pairs described by Einstein-Podolsky-Rosen. If entanglement can create geometry, then space-time may not be fundamental. It may be emergent from quantum information. This shifts our perspective entirely. Instead of asking how matter moves through space-time, we might ask how patterns of information give rise to space-time. Instead of treating geometry as primary, we may need to treat information as the underlying substrate. But here we must be careful. The holographic principle is powerful, elegant, and supported by strong theoretical arguments. But it is not yet experimentally confirmed as a description of our universe. The most precise formulations exist in special kinds of space-time geometries that differ from our observed cosmic expansion. Yet the idea remains compelling because it solves several deep problems. It limits the maximum amount of information that can exist in a region of space, preventing infinite densities. It offers insight into the black hole information paradox, and it suggests a route toward unifying gravity with quantum mechanics. If space-time is holographic, then what we perceive as three-dimensional reality may be a projection of deeper, lower-dimensional quantum processes. This does not mean our world is unreal. It means our description of it may not be fundamental. Temperature feels fundamental until we discover atoms. Perhaps space-time feels fundamental until we discover quantum information beneath it. The deeper implication is both unsettling and beautiful. What if space is not something you move through, but something that emerges from relationships between quantum systems? What if distance itself is a measure of entanglement? In some theoretical models, the more entangled two regions are, the closer they are in space-time geometry. Reduce entanglement, and the geometry stretches. If this is true, then geometry is not primary. Connectivity is, and this would explain why our attempts to quantize space-time directly fail. We may be trying to quantize something that is already emergent, like trying to quantize the shape of a wave without understanding the water beneath it. And this brings us back to our central mystery. Why don't we understand space-time yet? Because space-time may not be the foundation, it may be the consequence. If true, then our most basic intuition, that space exists as a stage and time flows independently, may be an effective illusion arising from deeper quantum laws. We have bent space-time in equations. We have measured its ripples. We have confirmed its curvature around stars. But we may not yet know what it is made of, or whether it is made of anything at all. We experience time as movement. We remember the past. We feel the present. We anticipate the future. Our time seems to flow like a river, carrying us forward from moment to moment. It feels directional, irreversible, and deeply personal. But when we examine space-time through the lens of relativity, that familiar flow begins to dissolve. In Einstein's framework, space-time is a four-dimensional structure. Every event, past, present, and future, exists as a point within that structure. The equations of relativity do not distinguish between past and future. They treat time as another dimension, similar in many ways to space. This leads to a profound implication known as the block universe. In the block universe view, space-time is like a complete geometric object. All events, the formation of Earth, your birth, distant supernovae, and future moments not yet experienced, coexist within the four-dimensional structure. Nothing moves through space-time. Instead, everything simply exists within it. Your sense of the present moment may not correspond to an objective, universal now. In relativity, simultaneity is relative. Two observers moving relative to one another may disagree about whether two distant events occurred at the same time. There is no universal clock synchronizing the cosmos. If there is no universal present, then what is the present? In the block universe interpretation, the present is not a global slice through space-time. It is a perspective, a local experience of a particular world line. A world line is the path an object traces through space-time. Your entire life, from birth to death, is a continuous line embedded in space-time geometry. You experience that line sequentially, but the line itself simply exists. This challenges our deepest intuition. If the future already exists in space-time, what does that mean for free will? If time does not objectively flow, what is the sensation of flow? Some physicists argue that the flow of time is emergent, a consequence of entropy and thermodynamics. The second law of thermodynamics tells us that entropy tends to increase. This gives rise to the arrow of time. We remember the past because it has lower entropy, and we move toward the future because entropy increases. But the fundamental equations of physics, including general relativity and most of quantum mechanics, are time-symmetric. They do not inherently prefer past over future. The asymmetry we experience may arise from boundary conditions, specifically the low entropy state of the early universe. So is time fundamental, or is it emergent, unlike temperature? In some approaches to quantum gravity, time may not exist at the deepest level. Certain equations describing the universe at fundamental scales lack an explicit time variable. Instead, time may emerge from relationships between quantum states. If this is true, then time, like space-time itself, may not be a basic ingredient of reality. It may arise from deeper dynamics. The block universe view is not universally accepted. Some philosophers and physicists advocate for presentism, the idea that only the present is real. Others support eternalism, consistent with relativity, where past and future are equally real. But relativity strongly supports the idea that there is no absolute present. This does not mean that experience is illusory, but it means that our experience of time may be a feature of consciousness interacting with space-time, rather than a property of space-time itself. Consider this carefully. If space-time is a static four-dimensional structure, and time does not objectively flow, then what we call change is simply our traversal along our world line. The universe does not evolve in time. It is. This is deeply counterintuitive. Yet the mathematics of relativity allows, and perhaps even suggests, such an interpretation. And if space-time itself may be emergent from quantum information, and time may be emergent from entropy or relational dynamics, then our most basic intuitions about reality may be layered approximations. We evolve to perceive time as flowing because that perception is adaptive. But at the deepest level, time may be more like a dimension, static, unlaid out, complete. This realization brings us closer to the core mystery. Why don't we understand space-time yet? Because space-time is not just geometry. It contains within it the puzzle of time. And time is entangled with causality, memory, entropy, and consciousness. We have equations describing how space-time bends. We have theories suggesting space-time emerges from quantum information. But we do not yet know whether time itself is fundamental or derivative. For centuries, humanity believed the universe was static. The stars seemed fixed. The heavens appeared eternal. Space itself felt unmoving. Even Einstein, after completing general relativity, initially assumed the universe must be stable and unchanging on the largest scales. His equations, however, did not agree. When applied to the universe as a whole, general relativity suggested something extraordinary. Space-time itself could expand or contract. At first, Einstein resisted this implication. He introduced a mathematical adjustment known as the cosmological constant to keep the universe static. But in the 1920s, observations by Edwin Hubble revealed that distant galaxies are moving away from us. The farther away they are, the faster they recede. The universe is expanding, not because galaxies are flying through space like debris from an explosion, but because space itself is stretching. This distinction is subtle, yet profound. When we say the universe is expanding, we do not mean galaxies are moving into empty space. We mean the metric that defines distance between points is changing over time. The fabric of space-time is stretching, carrying galaxies with it. Imagine dots drawn on the surface of an inflating balloon. As the balloon expands, the dots move apart. Not because they are crawling across the surface, but because the surface itself is stretching. This is how cosmic expansion works. Space-time is dynamic not only near massive objects, but on the scale of the entire cosmos. And the story grows even stranger. In 1998, astronomers discovered that the expansion of the universe is not slowing down under gravity as once expected. It is accelerating. Something is driving space-time to stretch faster and faster. We call it dark energy. But that name is not an explanation. It is a placeholder for ignorance. Dark energy appears to permeate all of space-time. It does not clump like matter. It does not interact strongly with light. Yet, it exerts a repulsive effect on cosmic scales, and causing expansion to accelerate. And here is where space-time becomes even more mysterious. If dark energy is represented by the cosmological constant, a property of empty space itself, then empty space possesses energy. Even in regions devoid of matter, space-time carries an intrinsic energy density. Vacuum is not nothing. It has structure. Quantum field theory also predicts that empty space should have vacuum energy due to quantum fluctuations. But when physicists calculate this vacuum energy, the predicted value differs from the observed value of dark energy by an enormous factor. Often described as the worst theoretical prediction in physics. This discrepancy reveals something profound. We do not understand empty space-time. At cosmological scales, space-time is not static. It expands. Its expansion accelerates. It carries energy even in vacuum. At small scales, space-time may fluctuate quantum mechanically. At extreme curvature, space-time breaks down into singularities. At intermediate scales, it behaves smoothly and predictably. It bends, it ripples, it stretches. Space-time is not merely a background. It is active, dynamic, evolving. The expanding universe also reshapes our understanding of time. In cosmology, time has a beginning, at least in our current models. If we trace expansion backward, the universe becomes denser and hotter. Eventually, we reach a state where classical general relativity predicts a singularity, the Big Bang. But as with black holes, the singularity signals a breakdown of the theory. At the earliest moments of the universe, quantum gravity effects should dominate. But space-time itself may have emerged from a more fundamental quantum state. Did space-time begin at the Big Bang? Or did it transition from something deeper? Some models suggest the Big Bang was not a beginning, but a bounce, a transition from a previous phase of contraction. Others propose that space-time emerged from a quantum vacuum state, crystallizing as the universe cooled. The accelerating expansion driven by dark energy adds another layer to the puzzle. If dark energy continues to dominate, the universe will expand forever. Galaxies will drift beyond each other's observable horizons. Stars will burn out. Space-time will stretch into increasing isolation. And yet, even in this cosmic vastness, space-time remains structured by laws we partially understand and partially do not. We can measure expansion precisely. We can map cosmic microwave background radiation. We can observe large-scale structure across billions of light years. But we do not know what dark energy truly is. We do not know why vacuum energy has the value it does. We do not know whether space-time's expansion is driven by a constant property or by a dynamic field that evolves over time. Once again, space-time behaves in ways we can describe mathematically, but not fully explain physically. It curves around stars. It collapses into black holes. It fluctuates at quantum scales. It expands across cosmic distances. And yet, beneath all this behavior, we still do not know what space-time fundamentally is. Perhaps it is geometry. Perhaps it is information. Perhaps it is emergent. Perhaps it is something we have not yet imagined. If space-time bends, stretches, fluctuates, what impossibly emerges from something deeper? Then we must ask the question that sits quietly behind all others. Did space-time begin? Modern cosmology tells us that the universe has been expanding for approximately 13.8 billion years. When we trace that expansion backward using general relativity, distances shrink, temperatures rise, and densities increase. Eventually, we reach a point where the mathematics predicts a state of infinite density and curvature, the Big Bang singularity. But just as with black holes, the word singularity does not mean we have found an ultimate answer. It means our equations have failed. The singularity is not a physical object we can point to. It is a signal that general relativity cannot describe conditions at extremely small scales and extremely high energies. At the earliest fraction of a second, around 10 to the power of minus 43 seconds after what we call the Big Bang, the Planck time, quantum gravitational effects would dominate. Before that moment, our current theories cannot reliably describe what happened. So did space-time itself begin at that moment? Or is the Big Bang simply a transition from something more fundamental? In Einstein's equations, time is a dimension embedded within space-time. If space-time begins at the Big Bang, then time itself begins there as well. Asking what happened before the Big Bang may be like asking what is north of the North Pole. The question may not be meaningful within the framework. But this conclusion is not universally accepted. Some cosmological models attempt to avoid a true beginning. In certain quantum gravity approaches, The Big Bang may not be a singularity, but a bounce. A previous universe may have contracted to a minimum size before expanding again. In such models, space-time continues through the bounce, rather than emerging from nothing. Other proposals suggest that space-time itself emerged from a quantum state without classical geometry. In these scenarios, the early universe may have been described purely by quantum relationships, with space-time crystallizing as the system cooled and decohered. There are also inflationary models, which propose that a rapid exponential expansion occurred in the earliest moments, smoothing out irregularities and shaping the structure we observe today. Inflation itself may arise from quantum fields interacting with space-time geometry. Yet even inflation does not fully explain the origin of space-time. We still face a deeper mystery. Why does space-time exist at all? Why does it have 3 spatial dimensions and 1 time dimension? Why does it obey Einstein's equations at large scales? Why does it allow quantum fields to exist within it? These are not questions of measurement. They are questions of foundations. When we push our theories back to the earliest measurable moment, we encounter a boundary of ignorance. Cosmic microwave background radiation provides a snapshot of the universe approximately 380,000 years after the Big Bang. Particle physics allows us to describe processes up to fractions of a second after the beginning. But before the Planck time, we do not yet know. If space-time emerged, then there was a regime in which there was no space-time, no distance, no duration, no geometry, just a deeper, pre-geometric structure. This is difficult to imagine because our minds are shaped by space-time. We think in terms of location and sequence. But if space-time is emergent, then it may not be fundamental. And this possibility is one of the main reasons we do not fully understand space-time. We understand how it behaves under many conditions. We can describe cosmic expansion with remarkable precision. We can predict gravitational lensing and black hole mergers. But when we ask how space-time itself originated, we reach theoretical speculation. Some theories propose that space-time may arise from networks of quantum entanglement. Others suggest it may be a manifestation of more abstract mathematical structures. There are even proposals that space-time may be secondary to computational or informational processes at a deeper level. But none of these ideas are yet confirmed. The origin of space-time remains open, and so we find ourselves in a curious position. We have mapped galaxies billions of light years away. We have detected ripples in space-time from merging black holes. We have calculated time dilation with atomic precision. Yet we do not know whether space-time had a beginning, or whether it is an emergent phenomenon from something beyond our current models. Perhaps space-time began with the Big Bang. Perhaps it is eternal in some higher dimensional sense. Perhaps it is part of a multiverse where different regions obey different geometric laws. Or perhaps we are missing an entirely different framework that reframes the question itself. The beginning of time is not simply a cosmological problem. It is a conceptual one. If space-time began, then the origin of space-time is the origin of causality, structure, and physical law. If space-time is emergent, then what we call the beginning may simply be the first moment when geometry stabilized enough to behave classically. And so, once again, our journey returns to uncertainty. Not ignorance born of lack of effort, but uncertainty born of depth. Space-time is not a simple container. It curves, it stretches, it fluctuates. It may emerge, and it may have begun or transformed in ways we have yet to fully comprehend. After traveling through relativity, quantum mechanics, black holes, cosmic expansion, and the origin of time itself, we arrive at a question that feels almost unsettling in its simplicity. Is space-time truly fundamental? Or is it something that arises from deeper layers of reality? For most of modern physics, space-time has been treated as the stage upon which everything happens. Matter moves through it. Fields exist within it. Light travels across it. Gravity bends it. Even quantum fields are typically defined with respect to space-time coordinates. But what if space-time is not the stage? What if it is part of the performance? Over the past few decades, theoretical physics has begun to entertain the idea that space-time may be emergent, meaning it arises from something more basic, much like temperature arises from molecular motion or solidity arises from atomic bonds. No single atom possesses temperature. Temperature emerges from collective behavior. Could space-time be similar? In certain approaches to quantum gravity, space-time geometry appears to arise from quantum entanglement patterns. When two quantum systems are entangled, their states become correlated in a way that transcends classical intuition. Some mathematical models suggest that the strength and structure of entanglement may determine geometric relationships, effectively generating the connectivity we interpret as spatial proximity. In these frameworks, if entanglement between regions decreases, space-time distances increase. If entanglement vanishes entirely, space-time may disconnect. This implies something extraordinary. Space might be built from information. Distance might be a measure of correlation. Geometry might be emergent. Other approaches, such as loop quantum gravity, suggest that space-time has discrete building blocks, quantized chunks of area and volume. Instead of being infinitely divisible, space would have a smallest possible unit. Time, too, might advance in discrete steps at the most fundamental scale. In this picture, the smooth space-time we observe at large scales would be an approximation, like the smooth surface of a table that appears continuous, but is actually made of atoms. String theory offers yet another possibility. In that framework, the fundamental constituents of reality are tiny vibrating strings existing in higher dimensional space. The geometry of space-time emerges from how those strings vibrate and interact. Extra dimensions may exist beyond the familiar three of space and one of time, hidden at scales too small for direct detection. Each of these approaches attempts to solve the same problem: the incompatibility between quantum mechanics and general relativity. General relativity treats space-time as smooth and dynamic. Quantum mechanics treats fields and particles as probabilistic and discrete. If space-time itself must be quantized, then perhaps it is not fundamental. Or if it is fundamental, perhaps it obeys quantum principles in ways we have not yet discovered. The idea that space-time is emergent carries deep philosophical consequences. If space-time emerges from something more fundamental, then at the deepest level of reality, there may be no distance, no duration, no geometry at all, only abstract relationships or informational structures. Our experience of space, of here and there, would be an emergent property of deeper correlations. Our experience of time, of before and after, would arise from changes in entanglement, entropy, or quantum states. This does not make reality unreal. It makes it layered. While just as classical physics emerges from quantum mechanics at large scales, space-time itself may emerge from quantum processes at smaller scales. But here is the essential reason we still do not understand space-time. We have not yet experimentally confirmed any of these deeper structures. We do not know whether space-time is fundamentally continuous or discrete. We do not know whether it is primary or emergent. We do not know whether geometry arises from entanglement, strings, loops, or something entirely unforeseen. We stand at the boundary of knowledge. We can describe how space-time behaves. We can measure its curvature. We can detect its ripples. We can observe its expansion. But we cannot yet answer what it is. Perhaps future experiments, observations of quantum gravitational effects, measurements of black hole evaporation, and a detection of microscopic space-time structure will guide us toward clarity. Or perhaps understanding space-time will require a conceptual leap as radical as Einstein's was over a century ago. Because history teaches us something important. Newton believed space and time were absolute. Einstein showed they were relative and unified. We now suspect that space-time itself may not be fundamental. Each step has removed certainty and replaced it with deeper structure. And perhaps the next step will reveal that what we call space-time is only one layer of a more intricate reality. After everything we have explored, relativity, black holes, quantum mechanics, cosmic expansion, holography, emergence, the question remains quietly in the background. Why don't we understand space-time yet? It is not because we lack equations. General relativity predicts gravitational lensing, black hole mergers, and cosmic expansion with extraordinary precision. Quantum mechanics predicts atomic spectra and particle behavior with astonishing accuracy. Both theories are among the most successful scientific frameworks ever constructed. The problem is not failure. The problem is completeness. Space-time sits at the intersection of two pillars of physics that do not fully reconcile. On one side, general relativity describes a smooth, geometric continuum shaped by mass and energy. On the other side, quantum mechanics describes a probabilistic, fluctuating world built from discrete interactions. Each theory works within its own domain. But when we attempt to combine them, when gravity becomes strong at quantum scales, our mathematical tools falter. Black holes expose this gap. The Big Bang exposes this gap. The Planck scale exposes this gap. And so space-time remains partially understood because we do not yet possess a theory that unifies geometry and quantum uncertainty into a single coherent framework. But there is something deeper still. Even beyond the technical challenge of quantum gravity lies a conceptual one. Space-time is not just another physical object. It is the arena in which physical objects exist. To question space-time is to question the structure that makes questioning possible. Every experiment we perform assumes a spatial distance and a duration. Every measurement is embedded in space-time coordinates. Every observation unfolds within it. So how do we step outside space-time to analyze it? We cannot. We can only infer its properties from within. This is why progress is slow and subtle. When Einstein replaced absolute space and time with curved space-time, he did not simply adjust a parameter. He reshaped the conceptual foundation of physics. Space and time were no longer independent. They became dynamic and relative. Now we suspect that space-time itself may not be fundamental. And this shift may require an equally profound transformation in our thinking. Perhaps space-time is not a substance. Perhaps it is not a fabric. Perhaps it is not even geometry in the most basic sense. Perhaps it is information, or relations, or something entirely beyond current language. The difficulty lies in the fact that our intuitions evolved in a world where space-time behaves classically. We perceive continuity, locality, and linear time because those approximations hold at human scales. But at cosmic scales, space-time stretches. At extreme densities, it collapses. At microscopic scales, it may fluctuate. At the earliest moments, it may not have existed in recognizable form. This layered behavior suggests that space-time might be an emergent phenomenon, stable and smooth at large scales, granular and uncertain at small scales. If that is true, then asking, "What is space-time?" may be like asking, "What is temperature?" before discovering atoms. We are glimpsing the macroscopic surface of a deeper, microscopic structure. And until we uncover that structure, space-time remains an incomplete story. There is also the mystery of why space-time has the properties it does. Why 3 spatial dimensions? Why 1 time dimension? Why Lorentzian geometry rather than some alternative? Why do Einstein's equations describe gravity so well? Why does dark energy exist? Or why does the vacuum possess energy at all? These are not minor adjustments within a finished framework. They are fundamental puzzles. And perhaps the reason space-time remains mysterious is because it is not merely a physical structure. It may be tied to deeper principles of information, symmetry, and existence itself. We have learned how space-time behaves. We have bent it in equations. We have watched it ripple. We have traced its expansion. But behavior is not identity. Knowing how something acts does not mean we know what it is. And that is where we stand. Space-time is measurable but not fully explainable. Observable but not fully reducible. Mathematically precise yet conceptually incomplete. And perhaps this is not a weakness of physics, but a sign of its depth. The closer we approach the foundations of reality, and the more subtle those foundations become. We began with a simple question. Why don't we understand space-time yet? Along the way, space-time transformed before us. It was once absolute and unmoving in Newton's universe, a silent stage on which matter played its role. Then Einstein revealed that space and time were intertwined, flexible, dynamic. Gravity became geometry. The stage itself began to bend. Later, quantum mechanics unsettled that geometry. At microscopic scales, reality trembled with uncertainty. Smooth curvature gave way to probabilistic fluctuations. And where gravity met quantum theory, our understanding fractured. Black holes showed us where space-time breaks. Cosmic expansion showed us that space-time stretches. Dark energy revealed that even emptiness carries weight. The Planck scale hinted that space-time may not be smooth at all. Holography suggested that space-time may be encoded elsewhere. And the block universe challenged whether time even flows. Each step took us deeper. And each step revealed that what seemed fundamental may not be. So why don't we understand space-time yet? Because space-time may not be the final layer. It may be an emergent structure arising from deeper principles we have only begun to glimpse. Information, entanglement, symmetry, quantum fields. These may sit beneath geometry itself. We are attempting to understand the framework that allows understanding. Every experiment, every equation, every observation assumes space-time. Yet we now suspect space-time may itself be a consequence of something more fundamental. That is why progress feels slow. Not because physics is failing, but because we are approaching the bedrock. And bedrock resists. Space-time behaves with extraordinary consistency at large scales. General relativity remains one of the most successful theories ever devised. Quantum mechanics continues to predict outcomes with astonishing precision. the universe unfolds according to rules that are coherent and testable. But coherence does not guarantee completeness. We may be living in a transitional moment in physics, much like the late 19th century, when classical mechanics appeared complete, yet light quietly refused to obey its rules. Perhaps space-time is our current ether, a concept that works beautifully at one level, but will eventually be replaced by something deeper. Or perhaps space-time will remain fundamental, but understood in a new way. Quantized, relational, informational. We do not yet know. And there is humility in that. For all our telescopes and accelerators, for all our satellites and detectors, the nature of space-time remains partially veiled. We have measured gravitational waves from colliding black holes billions of light years away. We have mapped the cosmic microwave background from nearly the dawn of time. We have tested time dilation with atomic clocks. And yet, the question remains open. What is space-time? Is it substance? Is it geometry? Is it emergent? Is it informational? Is it something our language cannot yet express? Perhaps the mystery persists because space-time is not just another object in the universe. It is the canvas of existence. To fully understand it may require rethinking what we mean by reality itself. And perhaps that is why this question continues to captivate physicists, named philosophers and dreamers alike. Because when we ask about space-time, we are not merely asking about distance and duration. We are asking about the structure of everything. And for now, the answer remains unfinished. Not unknown, not unknowable, but incomplete. The universe continues to curve and stretch. Black holes continue to ripple space-time. Galaxies continue to drift apart. Time continues to feel like it flows. And somewhere beneath all of it, the deeper structure waits to be uncovered. Until then, space-time remains both the most familiar and the most mysterious aspect of reality. The stage. The actor. There is another reason we may not fully understand space-time yet. And it has nothing to do with mathematics. It has to do with us. Human intuition evolved in a very specific environment: slow speeds, weak gravity, moderate distances, and a narrow temperature range. We evolved to navigate forests and plains, not event horizons in quantum foam. Our brains are tuned for survival, not for comprehending curved four-dimensional geometry. To us, space feels flat. Time feels constant. The present feels universal. But none of those intuitions survive close inspection. Special relativity tells us time slows down when you move fast. General relativity tells us time slows down near massive objects. Cosmology tells us space itself expands. Quantum mechanics tells us reality fluctuates beneath measurement. And yet, our daily experience contradicts all of this. You do not feel time dilation as you walk across a room. You do not sense curvature in the air around you. You do not perceive quantum uncertainty when you pick up a glass. And our senses filter reality into a stable approximation. But space-time may not be stable in the way it appears. It may only appear smooth because we are large compared to its smallest structure. It may only feel continuous because quantum discreteness averages out at human scales. It may only feel linear because entropy increases in one direction. Understanding space-time may require abandoning the very cognitive tools that make understanding possible. When Einstein proposed relativity, he relied heavily on thought experiments, trains, clocks, beams of light. He deliberately stepped outside intuition. He trusted mathematical consistency over common sense. And perhaps the next breakthrough will require the same. Because our difficulty in understanding space-time may not arise solely from missing equations, but from clinging to assumptions shaped by evolution. We expect space to be absolute because that is how it feels. We expect time to flow because that is how we experience memory. We expect cause to precede effect because that is how our nervous system encodes events. But physics repeatedly shows us that intuition is not authority. The deeper we look, the more reality resists ordinary perception. At high speeds, time slows. At strong gravity, clocks drift. At tiny scales, position dissolves into probability. At cosmic scales, space stretches. Perhaps space-time remains mysterious because it operates outside the range where intuition is reliable. We are trying to understand a framework far larger and smaller than anything our minds evolved to process. Even language struggles. We call space-time a fabric, but it is not cloth. We say it bends, but it does not fold like paper. We say it stretches, but it has no fibers. These metaphors are useful, but they are scaffolding, not substance. And sometimes scaffolding can limit what we imagine is possible. To truly understand space-time may require concepts that feel alien, just as curved Earth once felt absurd to flat Earth intuition, just as time dilation once felt impossible to classical reasoning, just as quantum superposition still feels paradoxical. History suggests something important. Each time physics advanced, it demanded a surrender of certainty. Absolute space gave way to relativity. Deterministic mechanics gave way to probability. Static universe gave way to expansion. Smooth geometry may give way to emergent information. Understanding space-time may not fail because reality is unknowable. It may simply demand intellectual humility. Because space-time is not an object among objects, it is the condition for objects. And unraveling the condition for existence itself is not a small task. Perhaps the reason we do not yet understand space-time is not that it is hiding from us. It is that we are still learning how to ask the right questions. For all the abstraction, for all the mathematics, physics ultimately returns to experiment. Ideas may be elegant. Equations may be beautiful. But until nature confirms them, they remain provisional. And so the question becomes, can we test space-time itself? In some sense, we already have. General relativity has been tested repeatedly for over a century. The bending of starlight during eclipses confirmed space-time curvature. The precise orbit of Mercury revealed deviations that Newton's laws could not explain. Atomic clocks on satellites confirm gravitational time dilation daily. Gravitational waves, ripples in space-time, have been detected from merging black holes and neutron stars billions of light years away. Space-time curves exactly as Einstein predicted. But these confirmations test space-time at large scales, where gravity dominates and quantum effects are negligible. The deeper mystery lies elsewhere. We need experiments that probe the intersection of gravity and quantum mechanics. And that is far more difficult. At ordinary energies, gravity is extraordinarily weak compared to the other fundamental forces. To detect quantum gravitational effects directly would require energies near the Planck scale, vastly beyond current technological capability. But physicists are not waiting passively. There are indirect paths. Some researchers search for tiny deviations in gravitational wave signals, subtle irregularities that might hint at quantum structure beneath space-time. If space-time were granular, perhaps high-frequency gravitational waves would reveal distortions inconsistent with smooth geometry. Others look to black holes. The Event Horizon Telescope has imaged the shadow of a black hole. Future observations may probe the structure near event horizons more precisely. If quantum effects alter the boundary in measurable ways, the data could reveal inconsistencies with classical general relativity. There are also laboratory approaches. Some experimentalists attempt to test whether gravity itself can create quantum entanglement. If two tiny masses placed near each other become entangled purely through gravitational interaction, that would suggest gravity, and therefore space-time curvature, possesses quantum properties. Such experiments are extraordinarily delicate. They push the limits of isolation and precision. But they are underway. Cosmology offers another window. The early universe was both hot and dense, where quantum effects and gravity overlapped. Subtle imprints in the cosmic microwave background radiation may contain traces of quantum gravitational phenomena. Primordial gravitational waves, if detected, could reveal how space-time behaved in the universe's first fractions of a second. Even dark energy may provide clues. If cosmic acceleration changes over time in ways inconsistent with a simple cosmological constant, and it might hint at deeper dynamical structure within space-time itself. And yet, for now, every test continues to affirm Einstein's equations at observable scales. Space-time behaves beautifully, but it behaves too beautifully. Because the real question is not whether space-time curves, it is what lies beneath the curvature. Experimentally probing that layer requires extraordinary patience. Science often advances not in leaps, but in refinements. A slight deviation, a tiny anomaly, a subtle inconsistency. And sometimes, those small cracks open revolutions. In the late 19th century, classical physics seemed complete until precise measurements of light speed revealed a problem. Perhaps space-time's next revelation will come not from grand theory, but from an unexpected discrepancy. A gravitational wave that behaves slightly differently than predicted. A black hole image that reveals subtle structure. A laboratory experiment that confirms gravity entangles quantum systems. Until then, space-time remains consistent at accessible scales. But consistency does not equal finality. It means we have mapped one layer. The deeper layers remain hidden. And perhaps the ultimate theory of space-time will not resemble general relativity or quantum mechanics as we know them. It may require a conceptual shift as profound as Einstein's. A new language for describing reality. Because the challenge is immense. We are not merely trying to unify forces. We are trying to unify the framework in which forces exist. And so we continue measuring, listening to gravitational waves, observing distant galaxies, testing quantum systems, waiting for space-time itself to reveal where our current understanding begins to fracture. For more than a century, physicists have carried a quiet dream, a single framework, a unified description, one set of principles that explains gravity, quantum mechanics, matter, energy, and the very structure of space-time itself. This dream is often called the theory of everything. But the phrase can be misleading. It does not mean explaining love, consciousness, or human experience. It means something more specific, a complete and internally consistent physical theory that unifies general relativity and quantum mechanics. Because at present, we live with two extraordinarily successful but fundamentally incompatible descriptions of reality. General relativity describes gravity as the curvature of space-time. It works beautifully at cosmic scales. It predicts black holes, gravitational waves, and the expansion of the universe with astonishing accuracy. Quantum mechanics describes the microscopic world of particles and fields. It governs atoms, radiation, and the fundamental forces, except gravity, with equally astonishing precision. Both theories are correct within their domains, but they are written in different mathematical languages. General relativity is geometric and continuous. Quantum mechanics is probabilistic and discrete. When we try to apply quantum principles to gravity, to quantize space-time itself, infinities appear that cannot be resolved using standard techniques. The mathematics breaks down. This breakdown is not subtle, it is structural. And so the search for a deeper theory continues. String theory is one of the most ambitious attempts, when it proposes that the fundamental constituents of reality are not point-like particles, but tiny vibrating strings. Different vibrational modes correspond to different particles. Gravity naturally appears within this framework as one of those vibrational patterns. In string theory, extra spatial dimensions are required for mathematical consistency. These dimensions may be compactified, curled up at scales too small to observe directly. Loop quantum gravity takes a different approach. Instead of replacing particles with strings, it attempts to quantize space-time geometry itself. In this picture, space is composed of discrete units connected in a network, a spin network, forming the underlying structure from which smooth geometry emerges. Other approaches exist as well. Causal dynamical triangulations, asymptotic safety, the emergent gravity models, holographic dualities. Each is an attempt to answer the same fundamental question: what is space-time made of? Or perhaps more precisely, is space-time made of anything at all? The search for a unified theory faces enormous challenges. Experimental verification is difficult because quantum gravitational effects occur at energies far beyond current technological reach. The Planck scale remains inaccessible. This means progress is driven largely by mathematical consistency and indirect inference rather than direct measurement. And this is where humility enters. It is possible that the ultimate theory will not resemble any current candidate. It may require abandoning deeply held assumptions. Perhaps even the assumption that space-time is a fundamental arena, because some physicists suspect that the true foundation of reality may be informational rather than geometric. Others believe that quantum mechanics itself may require revision when gravity is fully incorporated. It is also possible that there is no single, simple, unifying equation. That reality may be layered in ways that resist reduction to one elegant formula. The phrase, theory of everything, suggests finality. But physics has a history of replacing final theories with deeper ones. Newton once seemed complete, then relativity reshaped space and time. Then quantum mechanics reshaped matter and energy. Perhaps space-time itself is the next layer to transform. And perhaps the goal is not to eliminate mystery, but to refine it, because understanding space-time fully would mean understanding the structure that underlies every physical process. It would clarify black holes. It would explain the Big Bang. It would illuminate dark energy. It might even reshape our understanding of time itself. But until such a theory is experimentally confirmed, space-time remains an open question. Not undefined, not chaotic, but incomplete. The search continues not because our current theories fail, but because they succeed within limits. And those limits are precisely where space-time becomes most interesting. There is a possibility we rarely speak about openly. What if space-time is not just difficult to understand? what if there are fundamental limits to how deeply it can be understood? Physics has always progressed by pushing boundaries. Telescopes extended vision into deep space. Microscopes revealed hidden cellular worlds. Particle accelerators probed smaller and smaller structures. And in each time we built a better instrument, reality revealed another layer. But space-time presents a unique challenge. To probe its deepest structure directly would require energies near the Planck scale, energies so enormous that recreating them artificially may be permanently beyond technological reach. The universe itself achieved those energies only in its earliest fractions of a second. If certain scales are forever inaccessible, then our knowledge may rely entirely on indirect clues. And even indirect clues may face limits. Black holes, for example, hide information behind event horizons. If certain regions of space-time are causally disconnected from us, forever beyond observational reach, then part of reality may be fundamentally hidden. Cosmic expansion introduces another boundary. As the universe accelerates, and distant galaxies will eventually recede beyond our observable horizon, future observers may see only a small, isolated region of space-time, unaware of the vast cosmos that once existed. Information loss is not just theoretical. It may be cosmological. There are also theoretical limits. Quantum mechanics introduces uncertainty. The Heisenberg uncertainty principle prevents simultaneous precise knowledge of position and momentum. If space-time itself is subject to quantum uncertainty, then geometry may never be knowable with infinite precision. There may be a smallest measurable length, a smallest measurable time interval. If space-time is quantized, then continuity is an illusion at large scales, and precision has a limit. There are even deeper philosophical considerations. Gödel's incompleteness theorems show that in sufficiently complex mathematical systems, there are true statements that cannot be proven within the system itself. Physics relies on mathematics. Could it be that certain truths about space-time are unprovable within our conceptual framework? This does not imply ignorance. It implies structure. Just as there are limits to computation, there may be limits to physical description. But limits are not necessarily barriers. They are edges. And edges are where understanding transforms. Perhaps space-time cannot be described in a single complete equation because it is not a single-layer structure. Perhaps different scales require different languages. Classical geometry at large scales, quantum information at small scales, statistical emergence in between. Or perhaps the ultimate description will require a conceptual shift beyond geometry entirely, a framework where space and time are secondary constructs. The possibility of limits does not diminish science. It refines it. Understanding space-time may not mean reducing it to a simple formula. It may mean understanding how different descriptions interlock. It may mean accepting that certain features of reality are relational rather than absolute. It may mean embracing layered explanation rather than singular finality. The history of physics teaches something subtle. Each time we believed we had reached the foundation, another layer appeared beneath it. Perhaps space-time is not the deepest layer, or perhaps it is. But its depth includes boundaries we cannot cross. The mystery remains not because we lack intelligence or effort. It remains because space-time sits at the root of measurement itself. To understand it fully may require stepping outside the very structure that defines inside and outside. And that may not be entirely possible. Yet the pursuit continues. It's because even if complete understanding remains distant, Each refinement sharpens the picture. Each experiment clarifies behavior. Each equation tightens coherence. Each question deepens humility. And perhaps that humility is part of the answer. There is something extraordinary about the fact that we are able to question space-time at all. We are not outside observers examining a distant object. We are inside the very structure we are trying to understand. Every breath you take, every thought you have, every memory you carry, all of it unfolds within space-time. Your body curves space-time slightly, like your clocks tick at a slightly different rate than clocks on satellites. Gravitational waves from distant black holes pass through you unnoticed. The universe expands gently in all directions, even now. And yet, we move through this vast structure as though it were obvious. Space feels empty. Time feels steady. Reality feels stable. But beneath that familiarity lies one of the deepest unsolved questions in science. What is space-time? Not how it behaves, not how it bends, but what it truly is. Perhaps it is fundamental. Perhaps it is emergent. Perhaps it is informational. Perhaps it is layered in ways our language cannot yet capture. And maybe the reason we do not understand space-time yet is not because it is hiding, but because we are still learning how to see it. Humanity once believed Earth was stationary. We once believed time was universal. We once believed gravity was a force acting across empty space. Each belief felt certain. Each belief yielded to deeper understanding. And now, space-time itself stands at the frontier. If you've made it this far into the journey, take a quiet moment to appreciate something subtle. You are engaging with one of the deepest questions ever asked. And if explorations like this help you think more slowly, more deeply, consider subscribing to Science for Sleep. These long-form journeys are built for minds that enjoy drifting through difficult ideas without noise or hype. Because space-time deserves patience. Understanding it may take generations or centuries, or a conceptual leap none of us yet see. But the search continues. Researchers refine gravitational wave detectors. The cosmologists map the early universe with greater precision. Quantum physicists test whether gravity can entangle particles. Theoretical physicists build models where geometry emerges from information, step by step, layer by layer. The mystery narrows, even if it does not yet disappear. And perhaps that is enough. Space-time does not need to be fully understood to be profoundly beautiful. It curves to guide planets. It ripples to carry echoes of cosmic collisions. It stretches to shape galaxies. It allows existence itself. And within it, small, conscious beings ask questions about the structure that holds them. That, in itself, is remarkable. There is a horizon beyond which our understanding has not yet passed. Not a physical horizon like the edge of a black hole. Not a cosmic horizon where galaxies disappear from view, but an intellectual horizon. The boundary where our equations still work, yet our explanations remain incomplete. Space-time sits precisely at that boundary. We can describe how it curves. We can measure how it stretches. We can detect how it ripples. We can calculate how clocks drift in gravity and how light bends around massive objects. And yet, when we ask what space-time fundamentally is, we encounter silence. Perhaps space-time is the deepest layer of physical reality, the ultimate stage upon which everything unfolds. Or perhaps it is not a stage at all. Perhaps it is a consequence of deeper quantum relationships. Perhaps geometry is emergent from information. Perhaps time itself is not fundamental. but a pattern arising from entropy and change. These are not poetic speculations. They are serious scientific questions, and they remain open. But here is something quietly reassuring. Mystery is not failure. Mystery is the natural state at the frontier of knowledge. Newton did not fail because he did not know relativity. Einstein did not fail because he did not solve quantum gravity. Science is not a monument completed once and for all. It is a horizon that recedes as we approach it. Every time we believe we have reached the foundation, a deeper layer appears. And perhaps space-time is one of those layers. Or perhaps it is the last. If space-time is fundamental, then understanding it fully may reveal the final architecture of the universe. If space-time is emergent, then understanding it may require stepping into a new conceptual framework entirely, one where distance, duration, and geometry arise from something more abstract. Either way, the path forward demands patience, precision, humility, and imagination. Right now, as you listen, space-time continues its quiet work. It curves gently around Earth. It stretches imperceptibly between galaxies. It carries faint gravitational echoes from distant collisions. It allows atoms to hold together. It allows neurons to fire. It allows consciousness to ask questions about the structure that makes consciousness possible. That alone is extraordinary. We may not yet know whether space-time is smooth or granular at its core. We may not yet know whether time flows or simply exists. We may not yet know what dark energy truly is. But we do know this. The universe is coherent. It follows laws. It invites inquiry. And its deepest structures are not beyond thought, only beyond current understanding. One day, perhaps, a new framework will emerge, a new Einstein, a new mathematical insight, a subtle experimental anomaly that cracks the surface. And space-time will shift again, not in its behavior, but in our comprehension of it. Until then, we remain travelers within it, following our world lines through a structure vast beyond imagination, living briefly inside a geometry still unfolding in meaning. And perhaps that is the most beautiful part. We are not separate from space-time. We are expressions of it, temporary patterns within its grand structure, trying gently and persistently to understand the canvas that allows us to exist. For now, the mystery remains, not as a wall, but as a horizon. And horizons are meant to be approached slowly, curiously, patiently. Thank you for drifting through this question with me tonight. Final outro, drifting back through space-time. And so, we return to where we began. Space-time, the invisible structure beneath everything, remains both understood and mysterious. We can measure its curvature. We can detect its ripples. We can calculate its expansion. We can watch clocks tick differently in different gravitational fields. We can trace light bending around distant galaxies. And yet, we still do not know what it truly is. Perhaps space-time is fundamental, the deepest layer of reality. Perhaps it is emergent, a surface phenomenon arising from deeper quantum relationships. Perhaps time does not flow at all, but simply exists as part of a four-dimensional whole. Perhaps geometry itself is born from information. For now, these possibilities remain open. But there is something quietly beautiful in that openness. The universe is not finished in our understanding. The framework that holds stars, galaxies, and even our own thoughts together is still unfolding in the hands of human curiosity. And maybe that is exactly how it should be. Because the mystery of space-time is not a failure of knowledge. It is an invitation to keep looking deeper, to question what feels obvious, to remain comfortable with uncertainty. Right now, as you rest, space-time continues to curve around the Earth. Time moves differently in orbiting satellites. Gravitational waves pass silently through your body from events billions of light years away. The universe expands gently in every direction, all of it happening within a structure we only partially comprehend. And yet, it holds. Stable, quiet, precise. So as you drift towards sleep, must consider this gentle thought. We may not fully understand space-time yet, but we are part of it, embedded within it, carried along its geometry, living our brief paths through its vast structure. And somewhere in the future, whether already written in the block universe or still unfolding in quantum uncertainty, understanding will deepen. For now, the mystery remains. And that mystery is enough. Thank you for drifting through the fabric of reality with me tonight. Until our next quiet journey into the cosmos, rest gently.